Have you ever wondered how AI models get so ridiculously smart? Well, it's not all about those super complex algorithms. Today, we're going to pull back the curtain on the secret first step of any successful machine learning project. This is the unseen work, the data transformation journey. Let's get into it.
Everything, and I mean everything, starts with this one simple rule of computing: garbage in, garbage out. It basically means if you feed a model messy, junky data, you're going to get messy, junky results. Simple as that. In the age of AI, this isn't just some old saying, it's the absolute law.
So our goal here is to take you on a little journey. We're starting over on the left with this chaos. Raw data that's messy, inconsistent, and just full of noise. And we're going to transform it into this beautiful, pristine data set on the right, something that's clean, structured, and actually ready for an AI model to learn from. Think of it like turning a pile of random scrap metal into a finely tuned engine. Okay, so here's our game plan. We'll start with our guiding principle, garbage in, garbage out. Then we're going to put on our detective hats and investigate the data. After that, it's time to clean up the mess we find, pick our star players for the model, and finally, we'll wrap it all up by talking about why this whole process is the absolute foundation of trustworthy AI. Right. Before we can build anything cool, we have to approach our data kind of like a doctor. There are two key phases here. First, we have diagnosis, where we figure out what's actually wrong with the data, and then we have treatment, where we, go in and fix it. Now, these two phases have some official names you'll hear all the time. The diagnosis part, that's called exploratory data analysis, or just EDA. That's our detective work. The goal is just to understand. The treatment part is data preprocessing. This is our cleanup crew, the team that takes action. Their goal is to prepare. They're two sides of the same coin. You absolutely can't have one without the other. All right, detective time. Let's open up our case file. For this explainer, we're going to get our hands dirty with a data set all about drone flights. Our mission is to figure out what factors actually cause a drone's battery to drain faster.
And here's our first peek at the evidence. We've got a table here with a bunch of columns, or what data scientists call features. We're looking at things like wind speed, visibility, flight time, and the big one, the thing we're trying to predict: battery drain per minute.
So the first thing any data detective does is get a quick summary. And boom, right away we've got a clue. Out of 1,000 flight records, we can see that 20 of them are missing a value for wind speed, and 15 are missing visibility. These are literally holes in our story that we're going to have to patch up later. Next up, our detective gets this, a statistical report card. This thing gives us the average, the standard deviation, the min and max for every feature. Now, check this out. Look at the max value for battery drain. It's almost 50, but the average is way down around 14. That huge gap is another major clue. It's screaming at us that we might have some really extreme, unusual data points, what we call outliers. Okay, numbers on a table are fine, but to really, truly understand what's going on, we need to see it. Statistics alone can be misleading. We need to visualize the stuff. So let's start with a histogram for wind speed. See how the bars are all kind of the same height? This flat shape tells us something important. Our data set has flights from all sorts of weather, from really calm days to super windy ones. It's a nice, even spread. Now contrast that with visibility. See that big old hump right in the middle? That's a classic bell curve. And it shows us that most of these drone flights happened in really clear weather, with visibility clustered right around 8 to 10 kilometers. Average flight time looks kind of similar, right? Mostly centered around 15 to 20 minutes. But wait, do you see that? That little second bump way over on the right? That's interesting. It might be a clue that we're looking at two different types of missions, a bunch of short ones and then a small group of very long ones. And finally, here's our target variable, the battery drain. Most of the flights are clustered on the left, but look at that long tail stretching all the way out to the right. This pretty much confirms what we suspected earlier. Those data points way out there are extreme values. There are prime suspects for being outliers, and we definitely need to look into them.
And here we go. This is it, our first big breakthrough. When we plot battery drain against wind speed, look at that, a clear, straight line going up. This is that aha moment for our detective. It shows a really strong positive correlation. In simple terms, when the wind gets stronger, the battery drains faster. This is a powerful, powerful clue. Now let's compare that to visibility. When we plot battery drain against visibility, what do we get?
Nothing. It's just a random cloud of dots. There's no pattern, no relationship, nothing. This, my friends, is a dead end. Our detective can safely conclude that visibility probably isn't going to help us predict battery drain at all.
Okay, so our detective work is pretty much done. We found missing data, we've identified some suspicious outliers, and we know which clues actually lead somewhere. So now, it's time to call in the cleanup crew to get this data prepped and ready for our model.
So what about those missing values we found for wind speed and visibility? Well, we have two main ways to deal with them. We can just drop the entire record, just toss it out. Or we can do something called impute, which is just a fancy word for filling in that blank with a reasonable guess, like the average value. And let's not forget about these little troublemakers. You remember these points, right? The ones floating way, way above the main group? These are those outliers we spotted. The reason we care is that they can seriously mess with our model, pulling its predictions way off course. We've got to deal with them. So just to be clear, what exactly is an outlier? Well, it's just a data point that's way different from all the others. It could be a simple mistake, maybe a sensor glitched out, or it could be a real event that's just super rare. The hard part is figuring out which is which. And just like with missing data, we've got two main strategies here. We can just drop the outlier, get rid of it completely. That's a good move if you're pretty sure it's an error. Or we can clip it. This means we rein it in by capping its value at something more reasonable. This way, we keep the information that something extreme happened, but we don't let it totally skew our result. Okay, deep breath. The data is clean. Now for the final preparation step. We need to choose our starting lineup. We have to decide which of our features are the true star players, the ones that are going to help our model win, and which ones are just noise that we should probably leave on the bench. And this chart, a correlation matrix, makes that decision incredibly easy. It gives us a score for the relationship between each feature and our target, the battery drain. Just look at wind speed. It's got a score of 0.87. That's super close to 1, which means it has a really strong relationship. Now look at the others, like visibility and flight time. Their scores are almost 0. They're irrelevant noise. It's obvious, wind speed is our star player. So we've played detective, we've cleaned up the mess, we've picked our star features. But why did we go through all this trouble? Well, it's because this entire process, all this unseen work, builds the very foundation of reliable and trustworthy AI. And if you take one thing away from this, let it be this. Every single cleaning step we just took, dealing with missing values, clipping those outliers, it all has to be saved into a reusable process, a pipeline. And that pipeline has to be applied in the exact same way to any new data the model ever sees in the future. If it's not consistent, the model's predictions will be worthless. Consistency is absolutely everything. And that really just leaves us with one final question to think about. A model's real intelligence isn't just buried in its complex algorithms. It's built on the honesty and integrity of the data it learns from. So the next time you use an AI, ask yourself, is this thing telling me the truth, or is it just confidently repeating the hidden lies and errors that were buried in its raw data? The answer, as we've just seen, is all in the unseen work.